Hello, everyone, and this is a run-through of the Level 3 Physics Mechanics paper, 2024. If you've never taken an NCEA exam before, this is basically what the paper cover looks like, but I'm going to keep scrolling down so that we can go straight into the question. Question 1. Circular and rotational motion. A solid steel ball bearing with a radius of 7.00 millimeters and a mass 11.2 grams is released from different heights on a steel track. So this is the steel bearing, and we're told that it has a radius of 7.00 millimeter, as well as a mass of 11.2 grams. It is released from different heights on a steel track. It rolls down and then travels over a series of bumps. Each bump and dip has a radius of 35.0 millimeters. Now, from this name, circular and rotational, we can probably assume that we're dealing with circular motion and rotation of motion, and also from the fact that this track is all circly and stuff like that. Anyway, I'm going to go to part A question, sorry. So it says, in one trial, the ball bearing reaches the bottom of the first step with a velocity of 0.815 meters per second. Calculate the angular velocity of the ball bearing when it is at the bottom of the first step. So, what we want to know is the angular velocity. On your form of the sheet, it would be denoted as this little W looking. Look, that W. This is called omega. And we're given the radius of the ball, we're given the mass of the ball, and we're given the linear velocity of the ball. So, given all of these and looking at the formula sheet, we can use the equation on the formula sheet. Linear velocity equals radius multiplied by angular velocity. So, we're going to plug in our values. So the velocity is 0.850 meters per second, and the radius is 7.00 millimeters. Now you may be wondering, why am I using the 7.00 millimeters value rather than the 35.0 millimeters value? And that is a very good question. It is because we are using the radius of the object being rolled, not the radius of the path. It is the object being rolled, because this is angular motion, the rotational motion, blah, blah, blah. So we use the object's radius. And what we're going to do is, since this is in millimeters and we're dealing with meters per second, we're going to convert this millimeters into meters, like so. We divide it by 1,000. This is basic conversion. And then what we're going to get is omega equals 121.429. But we're not actually done here yet, right? We have three significant figures over here. We use three significant figures over here. So what we actually want to do is we want to round omega to three significant figures, because these little numbers over here could be a little bit unreliable. So omega equals 121 radians per second. And don't forget the units. This question gives you an achieved. Now we're going to do part B. So we're going to show that the maximum speed is 0.586 meters per second in order for the ball bearing to remain in contact with the track while going over the bump at point Y. Now point Y was when, I'm going to draw the track again, but basically this is point X and this is point Y. Y is at the very top. So this is really confusing, the X, Y, and all of that stuff, it's really hard to explain. And I went over to see the next question, and I think it might actually be better to do the next part question first, right? So first we're going to compare the forces acting at the top and bottom of each bump, and hence explain how the net force varies in these positions. So this compare, I was always said, a good strategy for these compare questions is to essentially do all the similarities and all the differences. So a similarity would be that net force provides the centripetal force, which is the force that keeps it going in circular motion. Net force provides the centripetal force. And this net force, assuming no gravity.
This idiot means assuming no friction.
Assuming no gravity. No gravity. And F net consists of two different components. It consists of the weight force, so we've got F, weight, as well as the reaction force, I'm pretty sure. But this reaction force is called the normal force, and it's basically perpendicular. Perpendicular meaning that it creates a 90-degree angle to the surface that the ball is on. So this is the reaction force. F net consists of resultant force and weight force. And then here we can say Fw is directed downwards. Now we're going to go all along and say all the differences. So at position X, the difference is that it's the centripetal force, which is always directed towards the center of the circle, right? These are the centers of the circles that I just drew. So at point X, the centripetal force is essentially directed upward. So Fc is directed upwards towards the center of the circle. Did I write too big? I think I did. Okay, I learned my lesson. Center, circle. And also, this reacted force is directed upwards, right? Because, as you can see, it is perpendicular to the surface that point X is on. If the ball was over here, the reactive force would actually be pointing. But here's the thing. So, reaction force is directed upwards. So, it must be larger than the weight force. And you might be wondering, why is that? Because we know from before that this, centripetal force is basically the net force, because the net force provides the centripetal force. So in point X, because the net force is directed upwards, that means that the force which is directed upwards must be larger than the force directed downward. That's why the reactant force is greater than the weight force. Okay? And then finally, because we get Fw directed away from center, from center, we actually get this. Centripetal force equals the reaction force minus the weight force. Because, the only components are the reacting force and the weight force. We don't have anything else. And we know that it's minus the weight force because it is away from the center. Now for Y, we basically write exactly the opposite as these bullet points over here. So we say the centripetal force is directed downwards this time. Here we go. See, it's directed downwards like so. So is directed downwards. Oh wait, I might want to label this a centrifugal force. Anyway, towards the center, the circle. Also, by the way, see how when I'm explaining, I'm dropping words such as the and all of that? I think this is actually a pretty neat strategy for physics because you don't necessarily have to be grammatically correct and all that stuff. And honestly, adding grammar wastes space, it wastes time, and if you're thinking really fast, you don't want to be adding grammar. So you can think about all of that and all that stuff in your head, but you don't actually have to write it down. Anyway, the reaction force is directed upwards as well, right? Right here, it's directed upwards. Upwards. So, remember, the weight force is directed downwards. So, we know that the net force is the total between the weight force and the reaction force. So what are we going to get? This. So this means that the weight force, which is the downwards force, must be larger than the reaction force, which is the upwards force, so that the net force can be downwards, and the net force is the centripetal force. Well, no, net force is not centripetal force, my bad. Net force provides centripetal force. Remember not to get them confused, because centripetal force is not something that you have, it's something that you need, okay? So pretty much, the weight force must be larger. The downwards force must be larger than the reactive force or the upwards force. So since the weight force is directed towards the center, what do we get? Centripetal force equals weight force minus reaction force, okay? Okay, now we're done with this question. So what gives you an achieve, what gives you a merit, what gives you an excellence? Basically, any one of these bullet points will give you an achieve. Any one of these bullet points, okay? Next, talk about the merit point. So to get merit, you either have to do all the similarities or the points of only x or the points of only y. So that means that even if you don't write any of these, like x and y, blah, 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 if you write all the similarities, you get merit. Like, contrarily, even if you don't write any similarities or any of the y points, but you write every single x point, you get a merit. So that's how you get a merit. But to get an excellence, you have to tick every single one of these bullet points. Okay? So, that's your achieved merit excellence. This is an excellence question, so it's quite important. Now I'm going to go up. So remember how I said this is at point y? And we know from the equation that we made before that the centripetal force is equal to the weight force minus the reactive force, because at the top of the bump or something like that, right? So that's how we know. Also, similarly, we can write it like this, but it's actually more like physically correct to state that Fw minus Fr provides Fc. Because remember, centripetal force is not something that you have, it's something that you need. That's basically a concept that you have to have engraved in your mind. Anyway, we're told that the maximum speed is 0.586 meters per second in order for the ball bearing to remain in contact with the track while going over the bump at point Y. The bump has a radius of 35.1 mm, but we already know this. Anyway, the maximum speed. So we're talking about the max speed. If you didn't know, at the max speed, the reaction force is 0. And the reason why is because you can basically, the reaction force is when something is touching a surface, right? So that means that the surface allows it to basically have a reaction force. It allows it to not fall, pretty much. But at the max speed, it travels fast enough so that it's basically kind of not touching, because it's just that vast, to be honest. And this allows this reaction force to not be there because it's not touching the surface. Also, like, contrarily, if you get, like, minimum speed, or, like, basically zero speed, it's going to be, like, so freaking slow. It's going to be completely touching the surface. So what you're going to get is the max reactive force. I just said flow or something like that. No, I mean, like, force, reactive force. Not bad. So we've got these two definitions, right? So what are we going to get? We're going to compile it into centripetal force equals weight force minus 0, because reaction force equals 0. And honestly, we can just take this away because minus 0 doesn't do anything. Now we're going to check our formula sheets and plug everything in. So NB squared over R, that's in your formula sheet, by the way, equals F weight, it's just mg. Where g is the gravitational constant. Now we can cancel mass from both sides, and what we get is v squared equals gravitational constant multiplied by the radius. And why are we not using the radius of the ball bearing and the radius of the bump? It's because this is the bump that we're traveling, okay? It's not like we're not using the radius 7.00 millimeters. We're using the radius of the bump because we are currently traveling on it, okay? So we're going to plug in our values. B squared equals 9.81 times 0.035. Oh, wait, do you not like this? Wait, sorry, I forgot to explain. This is in millimeters, so we have to convert it into, what is it? We have to convert it into meters. So I divided by 1,000. So from this, remember, we kind of actually more so looks like this. We get velocity equals 0.58596. But we're not done there. Remember, this is 3 significant figures. This is 3 significant figures. So what do we have to round it to? 3 significant figures. Honestly, I think schools kind of suck at teaching, like, all of these rounding rules. But they're actually quite important because you get all these little tiny things. And the thing is, practically, you're not going to get that kind of, like, precision, right? So that's why you have to, like, round it to, like, these smaller values. You know what I mean? So 3 significant figures, you can write that if you want. You don't have to. But I'm just going to write as required because this was show that the maximum speed is 0.586 meters per second. As you can see, we got 0.586 meters per second, so we're amazing. So we're going to go to by considering energy changes, calculate the maximum height h above the top of the first one. Is it weird to read all the questions out loud? I think, honestly, you can just read it in your head, and then I can, like, just kind of make you understand it. But, okay, so let's draw the ball again. The ball is at point Y, again, and it can be initially released from if it is to remain in contact with the track as it travels over the bumps. Wait, sorry. By considering energy changes, calculate the maximum height above the top of the first bump that the ball bearing can be initially released from if it is to remain in contact with the track. Oh, I see. See how they talk about height and all that stuff? When we talk about height, what does this imply? It always implies gravitational potential energy. So we're going to use this EP equation. Now, EP can be separated into, like, multiple different things because there's 2 different types of energy that we're considering. One being rotational kinetic energy and one being linear kinetic energy. Now we're going to look at our formula sheet and plug in the specific numbers that we have to plug in. So we've got mgh equals half of mvs. Wait, half of rotational inertia times rotational velocity squared plus half of nv square. So, honestly, we don't have the value of rotational velocity. Well, actually, we actually do. Wait, no, just pretend that we don't, okay? Just pretend that we don't. We don't have the rotational. I'm just sorry about that. So we don't have this value, and we don't have this value either. So what are we going to do? We're going to plug in other values. So we know that, rotational inertia equals 2 over 5 r squared from this equation right here. Thank you very much. And we also know from the equation V equals RW that omega equals V over R. So we're going to plug these into our equation like so. Now from here, it's a whole bunch of, I would say, like you need some math skills to be able to do this, but I just kind of expanded it from here to here, I'm pretty sure. And now what we can do is we can cancel this radius squared, and we can cancel these 2's to get 1 over 5 mgh equals 1 over 5 mv plus mv, it's mv squared, mv squared plus half of mv squared. And that's the same as 7 over 10 and the square. mgh equals 7 over 10 mb squared. So we cancel mass from both sides, and we get h equals 7 over 10 b squared divided by g, because we moved g to the other side. Now we can finally plug in our values. So h equals 7, and the velocity is 0.59596.
I forgot to show here that I squared the velocity.
If you're wondering how I got the velocity, it's from this unrounded version. For the working, we always use the unrounded version. It doesn't really matter how much you unround it to, but just try to unround it as much as possible. Like try to get this value here to as many significant figures as possible so that your answer over here can be more reliable. Okay, so we got h equals 0.0244999 blah blah blah. So we're going to round this because, as you can see, the lowest significant figure we have here is 3 significant figures. That means that we have to round it to 3 significant figures. So we have h equals 0.0245. Stop the meters. And that should be right. So what do we have here? Any one of these steps, if you think about this equation over here, or if you try to I don't know, if you just try to do something one step, you pretty much get your achieved. Okay? If you have a minor error, so you do all of this, but you make one little silly mistake, that's going to be me, by the way, and also you and stuff like that. Merit. And if you get this wonderful final answer, you get an excellence. So, for this question, to get an E8, you need 1 merit and 2 excellence, correct? Or 1 merit point and 2 excellence points. or 2 achieved points and 2 excellent points. Okay? I'm not going to go over the rest because we are all trying to aim for an E8, right? Question 2, rotational motion. So now we're not going to deal with any of that circular motion, centripetal force, blah, blah, blah. So a golf ball, so this golf ball over here, which has a mass of 0.0460 kg, is placed into a light cup that is attached to a flywheel with a diameter. So look, they're trying to trick us. See how they said diameter? Of 0.220 meters. This means that the radius is half of that, you know? So the radius is actually 0.110 meters. We're never going to use the diameter value. They're just trying to trick us by saying diameter instead of radius. Be careful. You always wanted to have the radius. Anyway. And it begins to accelerate downwards at a constant rate of 1.83 meters per second squared. Because of this meters, we know that this is the linear acceleration. So we have to show that the angular acceleration of the flywheel is 16.6 radians per second squared. If you look at your formula sheet, please look at your formula sheet, you will find, I'm pretty sure this is the formula. Linear acceleration equals the radius multiplied by the angular acceleration. So we're going to plug in our values. 1.83 equals 0.110 angular acceleration. So the angular acceleration equals, I'm going to put this into my calculator, 1.83 divided by 0.110 equals 16.6363. Now I haven't rounded it yet. We've got 3 significant figures here, 3 significant figures here. So the lowest significant figures we do 16.6, pretty much. And this is in radians per second square. And we say as required because this is a show that question. This is probably going to just get you untoothed if you get the right answer. If the bowling cups start from rest and fall through a distance of 0.750 meters, calculate the final angular velocity of flywheel. Okay, so I think what they want you to do is to notice that this distance is a linear value. So I think first of all, they want you to convert this distance into like radians pretty much. So we've got distance equals radians multiplied by, distance equals radius multiplied by radius. So we've got 0.750 over here. And then we've got 0.110 data. So theta equals 6.818181. And we're pretty familiar with rounding rules, right? No, but this is like part of our working, so we don't have to round it because this isn't our final answer. We only round the final answer. My bad. So what we want is the final angular velocity. So actually, from this, start from resting, when things start from rest, that means that the linear velocity, the angular velocity, the linear displacement, and the angular displacement all equal 0 initially. This means that the angular velocity, the initial angular velocity, equals 0. When we look at our formula sheet, we see this over here, right? Also, I forgot to say, but I totally recommend walking for the formula sheet on your hand. So that, you can actually trust me. Because what if these formulas aren't actually on the sheet for you? You know what I mean? Anyway. So we know the angular acceleration, which is here. We know the radians, and we know the initial angular velocity. That means that we can find out the final angular velocity, because as you can see, they asked for the final angular velocity. Honestly, it's getting really tired naming all of these variables, but I'm trying my hardest. So plug in our values. Remember, we use the unrounded value working out for the most reliable answer or the most accurate answer, whatever you want to say. And we also, remember, we've got this little thing over here, so that's the actual answer. And what do we get? We get... I have to plug this into my calculator. I feel like I have to plug this into my goddamn calculator. Oh man, I have to plug it in my calculator. So while you wait for me to plug it in my calculator, let's talk about the whole back thingies, maybe? I don't know. Anyway, okay, we got the answer. So the final angular velocity equals 15.061826. And we're familiar with rounding rules. Well, none of these were to 3 significant figures, but we know to round to 3 significant figures because of this here being 3 significant figures. So I'm going to round it to 3 significant figures and get 15.1 radians per second. And you can write 3 significant figures if you want to, but honestly, it doesn't really matter. Oh my god, I'm getting so tired. Calculate the rotational inertia of the flywheel. Begin your answer by calculating the force that is causing the flywheel to accelerate. Interesting. So, we have to talk about the force and all that stuff, right?
Okay.
Look at how nice my thing looks. Here's the ball. So what we have here is a downwards force of... We have the gravity being 9.8 meters per second square, right? But the actual acceleration was 1.83 meters per second square. So the net force, because that's what we saw practically, was 1.83 meters per second square. This means that there's a force that was acting on the flywheel, which caused the flywheel to accelerate, that made the net force 1.83 meters per second rather than 9.8 meters per second. So there's an upwards force of 9.8, minus 1.83. So I'm just going to plug this into my calculator. And this is the force that was acting on the flywheel. So 7.97 meters per second square. I just put this into my calculator. So this means that the force... Wait, did I say that is the force? Oh my goodness, that is the acceleration. My bad. This is the acceleration. But when we calculate the actual force, obviously it's mass times acceleration. And so the mass is 0.0 force. Whatever. I'm just going to write it. Should I write F equals ma? Or, yeah, I'll just write. Or should I write F equals m and then do g minus a? Obviously, we know that a here. Okay, I'll just do this. So F equals 0.046 multiplied by 7.97. And this gives us... No, I'm just going to leave it there, okay? Because Or should I... Well, I'm just contemplating everything. F equals 0.36662 newtons, and we're not going to round it because we need to calculate the rotational inertia of the flywheel. Now, if you look at your formula sheet, there are 2 different equations for torque, which is denoted as this symbol over here called tau. So there's force multiplied by radius, and there's also torque equals rotational inertia. Oh my God, that's what we want to find out. Multiplied by angular acceleration. Now, do you see something? Look. Now, the reason why I'm bringing in these like torque equations, even though we're not talking about torque at all, it's because if we have two equations for one thing, it's going to help us solve for the other thing. Let me tell you. Let me show you what this means. So either you can make these two equations equal each other, but I'm pretty sure NC usually wants you to find these like missing values. So I'm going to make torque equals this force value right over here multiplied by the radius. And now the radius was it like 0.110 or something, right? So the torque, and we're not going to round this, equals 0.040378. And now we're going to use this equation over here. So 0.0403788 torque equals rotational inertia multiplied by angular acceleration, which previously we found a 16.6363. If you want to go back, here we go. Rotational inner angle acceleration, 16.6363. Okay. You know, like the previous values that you like find and the previous values that you have used will always come in handy when you're like solving, essentially. And now we have rotational inertia equals 0.00243. I just want to two four. That was the round version. Sorry, 242,715, and then we round it and get for 3, and then we put units, kilogram meter squared. You might be wondering, where did these units come from? I'm just going to scroll up. See from this equation? Look, rotational inertia equals kilograms, because mass is measured in kilograms, and radius is measured in meters. So what are you going to get? Kilogram meters squared. Okay, this is like probably the best, Did I just zoom out? Oh my God, fuck me. I just zoomed out. That's really helpful. I zoomed out. Okay, what am I going to do? Okay. Wow, I just zoomed out. Okay, cool. Can we move on to the next question now? Explain what will happen to the final... Oh, wait. I never told you what this question was worth. I never said if it's a merit or an excellence. Oh my goodness gracious me. I am like totally falling off right now, and I'm really sorry about that. So, if you get this right, or if you, like try to plug things into this equation, you get an achieve. If you get the whole thing right, you get a merit. Now I'm going to go down to here. Now, for here, you use one of these equations over here. You get, what do you get? You get, an achieved. And if you get one mistake, one minor error, and this skews up your little thing up here, which is going to be us, by the way, you get a merit. And if you get the whole thing right, including the very last thing, you get an excellence. Okay, I'm really sorry for all the inconsistency and stuff. This is my first time existing on Earth, and this is my first, video, blah, blah, blah. And it's quite difficult, actually. It's quite difficult. And honestly, I don't really know. Anyway, explain what will happen to the final velocity of the bowling cup if the flywheel is replaced with a solid disc of the same radius and mass as that of the flywheel. Now, always when we have explain questions in physics, I'm pretty sure they always want us to talk about things that are, stayed constant. So we know that, earlier when we got that equation with, rotational inertia and like mass and radius and stuff like that, we kind of use that to show that rotational inertia is directly proportional to mass times radius squared. And we do this to say that if the disk is the same mass and radius, or do you want to say diameter? Doesn't really matter, to be honest, as the flywheel, the only difference. So see how we talked about what was constant? The only difference is the distribution of mass. Is distribution mass. I'm going to be talking in bullet points, and you're allowed to talk in bullet points for the actual exam. Totally 100%. In fact, it's actually recommended that you talk in bullet points because it helps with time. Anyway, so distribution of mass. Now, here's the thing. Let's draw a picture of a flywheel next to the picture of this. That's a really ugly flywheel. That doesn't even look like a flywheel. Okay. See how all the mass of the flywheel is concentrated around, like, well, this circle of here is called the axis of rotation, I'm pretty sure. This flywheel, all of the mass is like concentrated on the outside, like really far from the axis of rotation. So in the flywheel, the mass is actually on average distributed closer to the axis of rotation. And I think that's what they want you to write, right? In the flywheel, distribution of mass. Oh, in the flywheel, my bad. In the disk, the distribution of mass is on average closer. And you have to write on average because, I mean, you have lots of mass distributed here as well. Whereas you have like mass around here, I mean, you have to write on average because shapes can be inconsistent. Is on average closer to the axis of rotation. There we go. So, rotational inertia, this is something new, decreases. So what does this mean? Rotational inertia is basically the thing that like stops us from rotating, basically. And the more mass, which is spread further away from the axis of rotation, such as in the flywheel, the more rotational inertia, which means the harder it is for it to rotate. Now, a really good experiment would be to sit on like one of those like spinny chairs like this, and see how fast you roll when your arms and legs are tucked in. So when your mass is on average closer to the axis of rotation, and to spin when your hands and stuff are like all like, this is my arm, this is my body, all like spread out and stuff, which means that your axis of your mass is on the average further from your axis of rotation. And you're going to notice that when the mass is on average closer to the axis of rotation, your rotational inertia, well, not your rotational inertia, but you're going to spin faster. This means that it makes it easier for you to spin so that there's less rotational inertia. Okay? Now we're going to use equations, because physics really loves equations. So, let's get out this torque equation again. And why are we getting out this torque equation? Good question. Because we want to show, we want to rearrange it to this pretty much. Torque over blah, blah, blah. And from this equation, if K is constant, alpha is inversely proportional to I, thus decreasing rotational inertia like so increases in rotational acceleration. And then, also, I'm pretty sure, well, this writing, I wrote that tau is constant before this little, sorry about this, oh my god, I'm so tired, this little, like, proportional sign. But actually, I'm pretty sure it's better to write like this. So you have, thus, if radius is kept the same, it's constant, decreasing, increasing rotational acceleration. Now, increases linear acceleration. And this means, listen, we want to know what happens to final velocity, right? This means final velocity will be faster. Look at that chicken scratch. And what's going to get you an achieved merit excellent? Honestly, I don't really remember. If you find that the rotation, without reasoning, you find that the final velocity increases or that the rotational inertia decreases for the disk, you get an achieve. Okay, you get an achieve. And if you make one piece of reasoning, just one, you get a merit. And if you do this whole entire answer here, you get an excellence. So now we have simple harmonic motion. And I'm really tired. A ball bearing is released on a watch glass and rolls back and forth with a simple harmonic motion. The watch glass is shallow, semicircular glass bowl with a radius of curvature r blah blah blah. Okay, so we're going to be talking about the basics of simple harmonic motion, aren't we? So what do we have here? We have a tension force, pretty much. And here, what do we have? We also have, if the ball is here, we have a weight force, okay? Now I'm going to do vector addition to see where the net force is. And the net force in simple harmonic motion is also called the F restore force. And now, what's that? You may be wondering. It's just a restore force, to be honest. Yeah, the restoring force. So, like denoted, like F breast. So, how do we do vector addition again? So we have tension, we have weight, and then we have the restore force. And so we have, my thing is like not to scale, by the way, but F restore, this is the net force. So, and here, what do we have? The ball is going this way, pretty much, right? So this is the direction of like the ball or something. So, or direction of like the displacement. What you're going to get is state the two conditions necessary for the ball bearing to be considered some of them with simple harmonic motion. So one of them is that the restoring force, also from F equals ma, this is a vector, meaning it has a direction. This is a vector with meaning it has a direction. But this is a scalar, doesn't have a direction. So what you're going to get is that the direction of the restoring force is the same as the direction of the acceleration. So the restoring force, or the acceleration, and acceleration, I would say, is proportional to the displacement from equilibrium. Now, this is called equilibrium, right? in magnitude. We talk about magnitude, and then next we talk about direction. So the restoring force and acceleration is directed towards the equilibrium at all time. And interestingly, that is always the opposite direction. Opposite direction to the displacement. Direction to displacement. So the ball bearing is released 0. Okay. It says using reference circles or otherwise calculate the displacement of the ball bearing after 1.20 seconds. How do we use displacement circles? Honestly, we're going to turn this into like a dog. Okay? Because it's been a long day of physics and stuff, and we're all tired. So it's a dog. Calculate the displacement of the ball bearing after 1.20 seconds. How about no? Okay. Anyway. So we have y equals a cosine. Why does this omega t? Why do we use this? Because this is simple harmonic motion. Why did we use the cosine one instead of the sine one, you may be asking? Because they said it is released from the right of the equilibrium position. When it is released at the equilibrium position or something like that, we use sine. But when it's released from the right, we always use cosine. So, okay, so this is, this is what what are we trying to search for? We're trying to search for the displacement. And we know the value of A. It's just 0.0400 because it's the maximum, displacement. And that is 0.0400. And we know the time, right? But we actually, to know the displacement, we need to know one more thing. And that is this angular velocity thing. So we look at that from the sheet again, and what do we get? We find this value. And you may be wondering, why do we find this value over here? Because we know that the time period is 0.882, right? That's the only thing we haven't used. We want to use this capital letter T. And we know, okay, we're going to do even more plugging in, but F equals 1 over T. So that means that omega equals 2 pi over T. Now, it's much easier to do because now we have W equals A cosine 2 pi over T. And we know each and every single value here, so we know the value of y. So y equals 0.0400, 2 pi over 0.882 times 1.20, and so y equals negative 0.0256. So it is to the left of the equilibrium, because it's negative. And then we have to round it, obviously, to three decimal points, significant figures. And we can do that, or we can say 0.0256 meters to the left of the equilibrium position. And this, having the correct answer gives you an excellent, okay? Like the whole correct answer. Minimum error, merit. And if you find if you use any of these equations and you find a good value, you're going to get and achieve. Did I say what you get for this one? You're honestly only getting a chi here, and they use top-down But they don't use top-down marking. That's the thing. But what they do use is that if you get, like 2 excellences and 1 merit or something like that, honestly, you don't have to get this right as long as you get every single thing right, every other thing right? Right? But anyway, eventually the ball bearing comes to rest. Using the axis provider, draw a label graph of the displacement versus time for 5 complete oscillations that they said. So what do you want to do? I think we want to label like where the t is. So t, 2t. Well, because like, here's the thing. Like, even though what you're going to find is that amplitude decreases, but the period or the frequency doesn't, and we want that to stay constant. So yeah. And we start at 4, right? And we're going to draw this little dotted line to show that it is exponentially decaying. So, -4. Oh, yeah. And so we draw a cosine graph, right? So it kind of looks like this. Oh my goodness, I have to close my door. So it kind of looks like that, and this, and that. And honestly, even though this drawing is really shitty, the only point that you have to have is to show the dotted lines, which is exponential decay. The y starting at 4, so the start part, and the time and the period being constant. So you get all 3, you get a merit, but you only do 1 or 2, you get unkeyed. So we have to name this phenomena. It is called damping. So basically what you know is that as the ball bearing oscillates, EP and EP, so the gravitational potential energy and the kinetic energy. Is it gravitational? Yeah. Transform interchangeably. Changeably. I.e., at any point, the total energy in the system, because energy cannot be destroyed or created, equals potential energy plus kinetic energy. However, this is assuming that no energy is lost. But energy in reality, energy is lost. Is lost from the system due to the heat or sound friction from friction. So total energy decreases over time, right? So also from this, it's actually, you can elaborate by saying like, it's actually the kinetic energy which transforms into friction. Goddamn you, kinetic energy. And I think, you can kind of see it happening because as, things are in motion, they're going to hit all the other particles, and then that's going to like cause friction, and then it's going to slow down. And that was the worst diagram I've ever drawn in my life. So less E total means less gravitational potential energy. So each time, the amplitude decrease. And we are done. So, if you either get it was damping, or that there was loss of energy due to friction, or that amplitude decreases, any one of them you get an achieved, okay? If you get damping and any one of these 2 points, you get a merit. And if you get the full answer, obviously you get an excellent. So, yeah, the end. It's the end. Thank you. I'm gonna, make things better quality, and, hopefully, everything's gonna be better soon. But, this is my first time, and I have fun. Sure, thank you.